For most of human history, the universe seemed simple. The heavens followed predictable patterns. The earth beneath our feet felt solid, and time appeared to flow in one steady direction. Then came science, and with it revelations that shattered common sense. First, Isaac Newton showed that the cosmos ran on universal laws of motion and gravity, uniting falling apples with orbiting planets. Then centuries later, Albert Einstein redefined space and time themselves, proving that the universe is flexible, dynamic, and curved by energy and mass. It was a revolution that gave us black holes, expanding universe, and even the Big Bang. And yet beneath these grand theories, another revolution was quietly underway. At the smallest scales imaginable, the world of atoms and subatomic particles, reality refused to play by classical rules. Instead of certainty, scientists found probabilities. Instead of solid matter, they found fields of fluctuating energy. Instead of neat, predictable behavior, they discovered phenomena so counterintuitive, they border on the absurd. Particles in two places at once, matter. An antimatter emerging from nothing, in the very act of observation altering reality. This is the quantum universe. A place where Einstein's relativity breaks down, where space and time themselves dissolve into foam, and where we confront questions that may hold the key to everything. In this film, we'll dive into that bizarre frontier. We'll begin with the Planck epoch. The first instant after the Big Bang, when the universe was governed not by stars and galaxies, but by raw quantum energy. We'll examine strange objects like virtual particles and quantum vacuums, explore mysteries like string theory and quantum gravity, and see how quantum effects shape the very technology, biology of life on Earth. Finally, we'll ask what this means for our future, and whether reality itself may emerge from information at the deepest level. Before we begin, I want to acknowledge the traditional custodians of the land on which we find ourselves. The Wurundjeri people for the Melbourne crew, and the Gadigal people for the Sydney crew. I also want to acknowledge the elders, the late Professor Fred Channon, Dr. Richard Trujan, and Dr. Sue Black. We pay our respects to them and their ongoing connection to the land, the waters, and the people of this nation. We encourage you to learn about and respect the history, culture, and protocols of the traditional owners of the lands where you live, work, and play. So let's begin at the beginning, the Big Bang. When the universe was born, it was unimaginably hot and dense. But within a fraction of a second, quantum effects kicked in and began to sculpt the cosmos, within 10 to the minus 43rd of a second. The universe had inflated faster than the speed of light, an event known as inflation. This bizarre episode is thought to have smoothed out the universe on the largest scales, setting the stage for stars, galaxies, and you. But it also left an indelible imprint on reality itself. Inflationary particle physicist Andre Linde likens this period to a raging fire hose. Reality was fluid, dynamic, and infinitely malleable. But as the universe expanded and cooled, the hose constricted until it became a rigid pipe. Once inflation ended, the rules changed and things began to solidify. Protons, neutrons, and electrons combined to form the first atoms. Gravity pulled those atoms together and stars ignited, forming the cosmic scaffolding that brought our solar system into being. The hose became a garden hose, then a pipe, then a faucet, eventually flowing into the river of life. And yet, despite all the changes, the imprint of the quantum fire hose remains. Strange echoes of the inflationary era persist, hiding in plain sight. Take, for example, empty space, or more accurately, the vacuum, because even a vacuum is teeming with activity. Quantum mechanics tells us that empty space isn't truly empty, but rather a frothing mass of virtual particles that pop in and out of existence. These particles carry energy, and that energy warps the fabric of spacetime, creating the very thing that allows stars and galaxies to exist. This warping is the same phenomenon that causes black holes, but instead of being concentrated in one spot, it's spread out across the entire universe. This means that space itself is never flat. It's perpetually bubbling, writhing, and inflating. Space-time foam, and the implications are profound. This constant flux may be the key to understanding the deepest mysteries of physics, including quantum gravity, the holy grail of modern physics. string theory, and the missing unification of gravity with quantum mechanics. If we can understand the nature of this foam, we may find the key to everything. Unfortunately, we don't live in a quantum universe. Our everyday experience seems utterly divorced from this subatomic realm. So how do we bridge the gap? How does the quantum foam become the solid ground beneath our feet? The answer lies in the strange process of decoherence. As a quantum state interacts with its environment, it slowly loses its quantum properties, allowing everyday physics to reassert itself. But while decoherence may explain why we don't perceive the foam directly, it doesn't change the fact that the quantum realm is real. Its effects are all around us, from the transistors in our phones to the DNA in our bodies. Understanding how the quantum foam shapes our world could unlock new technologies beyond our wildest dreams. Technologies like quantum computing, which harnesses the power of superposition and entanglement to perform calculations that would take classical computers millions of years. Or quantum teleportation, which uses entanglement to transmit quantum information instantaneously over vast distances. These technologies are already being developed and put to use today. They're evidence that the quantum revolution is well underway, and they hint at a future where the boundaries between science fiction and reality are blurred. In the realm of quantum physics, where the very nature of reality is called into question, there exists a concept so profound it defies human comprehension: the Planck epoch. It's the moment when the universe was just 10 to the negative 43 seconds old. That's 1 followed by 40 to zeros and a minus 43. It's the tiniest fraction of a second after the Big Bang. This moment holds the key to understanding how the universe came into existence and comprehending the very essence of reality. Welcome to our show, where today we delve into the mysteries of the Planck epoch, the birth of the quantum universe. The Planck epoch, named after the brilliant physicist Max Planck, is more than just a scientific term. It's a gateway to the unknown, a portal to the very origins of our existence. Now, you might wonder, why should we care about understanding something we can't measure and perhaps never will? Here's why. The Planck epoch holds the answers to some of physics' biggest unanswered questions. The Big Bang theory tells us that our universe started from a hot, dense state and expanded outward. But what happened before that? What caused the Big Bang itself? The Planck epoch is the period that comes before the Big Bang, a moment so ancient that our current understanding of physics breaks down. When we look back in time, we can see the universe only a few 100,000 years after the Big Bang. This is when the cosmic microwave background radiation was released, providing us with a snapshot of the early universe. But what happened in the first few moments, specifically those first 10 to the negative 43 seconds? Well, that's the realm of the Planck epoch. We don't know much about it because our current theories can't explain it. But we believe that during the Planck epoch, space and time were intertwined in a way we can't fathom. Gravity was so strong that it overcame all other forces, squeezing matter into an incredibly small space. This isn't just a scientific curiosity. Understanding what happened during the Planck epoch could help us better understand the behavior of the universe today. It could also help us understand what happens inside black holes and at the center of the universe. You see, black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They're formed when massive stars collapse at the end of their lives. But what happens inside a black hole? How does gravity work at such extreme distances? Again, the answer lies in the Planck epoch. It was during this time that the fundamental forces of nature, including gravity, separated. But how did this happen? And how does it relate to black holes? Fortunately, we don't have a definitive answer yet. It's one of the biggest unsolved mysteries in physics today. To grasp the immensity of the Planck epoch, let's compare it to the age of the universe. As of 2023, the universe is estimated to be around 13.8 billion years old. And yet the Planck epoch lasted for only 10 to the negative 43 seconds. That's 1 followed by 42 zeros and a minus 43 seconds. It's a tiny fraction of a trillionth of a second. It's hard to imagine something so small being so significant. But the significance of the Planck epoch doesn't lie in its size. It lies in what happened during that time. It was during the Planck epoch that the universe went from being a dimensionless point to a vast expanse of spacetime. It was during this time that the laws of physics as we know them today came into being. The constants of nature that we take for granted, like the speed of light and the gravitational constant, were established during the Planck epoch. Even the matter that makes up our bodies, the atoms and molecules that define life itself, were forged in the fires of the early universe. All this happened during a time when the universe was smaller than a proton, the smallest particle we know of, and yet it contains the energy of everything we see today. It's a mind-boggling concept, but it's supported by evidence from the cosmic microwave background radiation. This is the oldest light in the universe, and it provides us with a window into the early universe. By studying the cosmic microwave background, astronomers have been able to map the distribution of matter in the early universe. And they found that the distribution of matter is not uniform. There are tiny variations in density, and these variations are thought to have been caused by quantum fluctuations during the Planck epoch. But the Planck epoch wasn't just a time of great change, it was also a time of great violence. The universe was filled with a primordial soup of particles and energy, and these particles were moving at incredible speeds. The temperature of the universe was so high that protons and neutrons couldn't form. They were moving around too fast. They would have broken each other apart. But as the universe expanded, the temperature dropped and the particles slowed down. Eventually, they were able to come together and form the nuclei of atoms. Now let's talk about space itself. During the Planck epoch, space wasn't empty. It was filled with a sea of particles and energy. But it wasn't continuous either. It was made up of tiny, almost unimaginably small bubbles. These bubbles were constantly forming and disappearing. It was a kind of quantum foam. And this wasn't just a quirk of the early universe. It's a prediction of our current theories. Spacetime is expected to be inherently uncertain at the smallest scales. This is due to a principle in quantum mechanics known as the Heisenberg uncertainty principle. This principle states that UHN know both the position and momentum of a particle with absolute certainty. The more accurately you know one, the less you know the other. This isn't just a limitation of our knowledge. It's a property of nature itself. So what does all this mean for our understanding of reality? First, it means that reality is more complex than we might think. It's not just a smooth, continuous space-time. It's a dynamic, ever-changing landscape. Second, it means that reality is more interconnected than we might think. What happens at one part of the universe is intimately related to what happens at other parts. And third, it means that reality is more uncertain than we might think. We can't predict the future with 100% accuracy. There's always a random element at play. To understand the quantum universe, we need to challenge our intuition. We need to be willing to question what we think we know about the world. We need to be open to the possibility that reality is stranger than we can imagine. And that's why the Planck epoch is so important. It's a reminder that the universe never ceases to amaze. It's a testament to the power of human curiosity and the endless mysteries that lie ahead. As we continue to explore the depths of space and time, we'll undoubtedly encounter phenomena that challenge our understanding of reality. But we can face these challenges with courage and wonder. We can marvel at the complexity and interconnectedness of the universe and embrace the inherent uncertainty that makes life so thrilling. So let us celebrate the Planck epoch, not just as a moment in time, but as a symbol of the boundless wonders that await us in the quantum universe. Let's wrap this up, shall we? We've journeyed to the dawn of time, to the Planck epoch, where the universe was in its infancy, where space and time were intertwined in a cosmic dance, where the very essence of reality was being formed. We've seen that this wasn't just a moment in time, but a moment of creation, a moment of change, a moment of violence and uncertainty. And yet it was in this moment, in this tiny, fleeting instant, that the universe as we know it took shape. It's a sobering thought, a humbling experience to realize that everything we see around us, everything we know and love, emerged from this primordial chaos. And yet it's not just a moment of the past, it's a key to the future. Understanding the Planck epoch is vital to understanding the deepest mysteries of the universe. It's the key to unraveling the behavior of black holes, the key to predicting the fate of the universe, the key to understanding the very nature of reality. As we continue to explore the depths of the quantum universe, we'll undoubtedly face many challenges. But we can face them knowing that we're not just explorers, but pioneers. We're not just scientists, but dreamers. And it all began with a tiny, unimaginable moment, the Planck epoch. Here's a thought experiment for you. Imagine the largest empty room you can, a space so big that light doesn't even take a millisecond to cross it. Now imagine making this room perfectly smooth, with no air molecules or dust particles or sound. We usually think of such a place as utterly empty, nothing more than silence and stillness. But what if there's more to this apparent vacancy? What if something is happening in this seeming nowhere? Welcome to the realm of virtual particles, quantum vacuum, and the Casimir effect. When we talk about objects, we usually mean something we can see, touch, or measure in some way. Think about a baseball, the earth, or the star shining up in the night sky. These objects seem solid and substantial. But at the atomic level, the story changes dramatically. Everything we know is made up of tiny particles like electrons and protons and neutrons. Yet even these elementary particles are not really elementary. They too have internal structures and are made up of smaller constituents called quarks. So the concept of an object has to be broadened. An apple, a galaxy, or even you and me are not just collections of particles, but more fundamentally, patterns of energy and force that come together to create the illusion of solidity. Now let's dive deeper into this energy pattern. Each type of particle has a corresponding field that permeates all of space. The simplest example is the electromagnetic field, which carries light and other forms of electromagnetic radiation. Electrons move through these fields, and their motion influences the fields around them. This interaction between particles and fields is one of the cornerstones of quantum theory. But what about empty space? Does it have fields? If so, how do they work? Here we enter the bizarre realm of quantum field theory and discover that empty space, a perfect vacuum, is anything but empty. At the foundation of quantum theory is the idea that everything is quantized, meaning that properties like energy come in discrete chunks or quanta. The smallest possible chunk of energy is called the zero-point energy, and it applies even to the vacuum. In other words, even in the apparent absence of matter, there is a minimum amount of energy present. In fact, quantum fields never fall to a complete standstill. They always maintain a tiny, unobservable tremor. It's as if even in the quietest room, there's a whisper of sound just below the threshold of hearing. This ceaseless quantum motion is not merely a theoretical curiosity. It has profound implications. For one thing, it suggests that empty space isn't truly empty. Instead, it teems with virtual particles that flicker in and out of existence. These particles are called virtual because they don't exist long enough to be detected. They are only seen as brief disturbances in quantum fields, like ripples spreading across the surface of a pond after a stone is tossed in. Despite their fleeting nature, virtual particles have very real consequences. They play a crucial role in how atoms hold together and interact with each other. They mediate the forces between particles, and they even give rise to what is known as the Casimir effect. The Casimir effect is a bizarre consequence of vacuum energy that occurs when two uncharged metal plates are placed very close to each other in a vacuum. Here's how it works. Because the plates are perfectly smooth, they reflect the quantum fluctuations of the vacuum energy back toward each other. As the distance between the plates decreases, the number of these reflected fluctuations increases. This builds up a pressure that pushes the plates together. The closer the plates are, the greater the pressure. In effect, the vacuum seems to exert a force as if it were a physical substance. The Casimir effect was first predicted in 1948 and was confirmed experimentally in 1997. It's a remarkable demonstration of how the vacuum can manifest itself physically. But why should you care about virtual particles, quantum vacuum, and the Casimir effect? What makes these topics worthy of your time and attention? Well, here's why. First, these phenomena are not just abstract theories. They have direct implications for the way we understand reality. They show that empty space is not just a passive background, but an active participant in the universe. The vacuum is full of energy, and this energy can affect the behavior of particles and even the structure of spacetime itself. Seconds. The study of virtual particles and the Casimir effect provides a window into the deepest mysteries of modern physics. For example, the cosmological constant problem, which asks why the observed acceleration of the universe is so much smaller than the value predicted by quantum field theory, or the holographic principle, which suggests that the information content of a region of space is stored on its boundary. By exploring these topics, we gain a deeper understanding of the fundamental nature of reality. We learn that the universe is stranger and more complex than we could have ever imagined. And third, the mathematics underlying virtual particles and the quantum vacuum is both beautiful and profound. It reveals the deep connections between different areas of physics, from classical mechanics to quantum theory to general relativity. By studying this mathematics, we not only learn about the nature of the universe, but also about the power and elegance of human thought. So let's return to our thought experiment with the empty room. Recall that we imagined removing everything from this room, all particles, all fields, all disturbances. Now we know that this is impossible. The vacuum itself is filled with virtual particles, and these particles have measurable effects. They push and pull on each other and on the boundaries of the room. They exert a pressure that distorts the very fabric of space. In other words, even in the absence of matter, there is activity, change, and evolution. The universe is never empty. It is always full of possibilities. So the next time you find yourself in an empty room or an empty space, remember that what appears to be vacant may actually be teeming with life. You just need to know where to look. And what you see depends on the scale you choose. Let's zoom in a little. At a length scale of about 10 to the minus 13 centimeters, the realm of virtual particles emerges. Here the vacuum is a sea of fleeting disturbances, creating and annihilating particles in an endless cycle. A bit closer, at 10 to the minus 26 centimeters, we enter the realm of the Planck scale. Here quantum effects dominate, blurring the distinction between particle and wave. And at the even tinier level of 10 to the minus 33 centimeters, the limits of current theories are reached. Here spacetime itself seems to break down, giving way to a new, more fundamental structure. And if we were to continue zooming in, who knows what wonders we might uncover? Maybe the very atoms that make up our universe are themselves made of smaller constituents. Or perhaps they are merely shadows cast by deeper, more fundamental realities. The truth is that the universe never ceases to amaze. Its depths are fathomless, and its beauty is beyond compare. As we continue to explore the quantum vacuum and virtual particles, we must keep in mind that there are still many things we don't understand. Many questions that once seemed settled are now being reopened. For example, the role of the vacuum in cosmology, or the relationship between quantum fluctuations and the emergence of large-scale structures in the universe. There are also many areas that remain completely unexplored, such as the behavior of virtual particles in curved spacetime or the effects of quantum gravity. These are some of the frontier problems in physics today. We live in a time when new discoveries are being made at an incredible pace. Who knows what the future may hold? Perhaps we will find that the vacuum is not merely a stage for reality, but a participant in it. Or maybe it is the source of all creation, giving rise to the very matter and energy that make up the universe. The possibilities are endless. So keep your mind open and your curiosity alive. And who knows what you might discover? Maybe you will find the answer to one of the deepest mysteries of the cosmos. The study of the quantum vacuum and virtual particles is one of the most exciting and challenging areas of research in modern physics. It is a field that requires expertise in several areas, including quantum mechanics, field theory, general relativity, and cosmology. Fortunately, there are many resources available to help you get started. If you want to learn more about the quantum vacuum and virtual particles, here are some suggestions. Start with some introductory courses on quantum mechanics and special relativity. Once you have a good understanding of these topics, you can move on to more advanced courses on quantum field theory and general relativity. Some online courses that can help you get started include those offered by various universities and online learning platforms. These courses cover topics such as quantum mechanics, special relativity, quantum field theory, and cosmology. They are designed for students at various levels, from beginners to advanced learners. Another great resource is the library. There are many books that cover the basics of quantum mechanics and general relativity. Once you have a good understanding of these topics, you can move on to more advanced texts on quantum field theory and cosmology. In addition to these resources, there are also many excellent documentaries and videos available on YouTube that can help you learn about the quantum vacuum and virtual particles. Some notable examples include those produced by educational channels. Overall, the key to learning about the quantum vacuum and virtual particles is to start with the basics and build up from there. The fabric of reality is under construction. The brilliant physicists who make sense of our universe are telling us that the ground beneath our feet, the chair you're sitting on, the phone you're watching this on, all of it is made out of quantum foam. This means that even seemingly empty space is filled with energy, brimming with virtual particles popping in and out of existence, constantly shifting and changing. This is the world revealed by quantum mechanics, the theory that describes the tiniest building blocks of nature. But there's a problem. It doesn't play nicely with gravity. Gravity, as Einstein told us, warps the very structure of spacetime. That warp is what we feel as the force of gravity. But spacetime isn't supposed to warp. It's supposed to be flat and unchanging. At least that's what quantum mechanics says. How can we possibly make sense of a universe where empty space is both a seething mass of energy and a smooth, unchanging fabric? In today's video, we explore the strange and surprising insights from the frontier of physics. Welcome to Show Space. When we look at everyday objects like planets and stars, they seem solid and unchanging. But according to quantum mechanics, everything we see is really a fog of particles. We can't see these particles because they're too small. They're called elementary particles, and they include familiar ones like electrons and quarks, which make up protons and neutrons, which in turn make up atomic nuclei. But there are also less familiar particles in this quantum fog, like neutrinos and photons, and ones we don't even know about yet. Some of these particles buzz around freely. Others are bound up inside larger particles, which themselves are grouped together in giant assemblies that make up the stuff of stars and planets and galaxies. But here's where things get weird. According to quantum mechanics, all these particles exist in a haze of probability. You can only say that a particle has a certain momentum or position with some degree of uncertainty. Knowing one of these properties precisely, like position, means you know nothing about the other, like momentum. For example, if you were to measure the exact location of an electron, you would have no idea which direction it's moving. So this quantum fog is not static. The particles are always in motion, and this motion is governed by the same principles of fuzziness. You can't know exactly where a particle is and where it's going at the same time. This constant motion makes the particles in the quantum fog carry energy, and that energy fills all of space. This is the quantum vacuum. It's everywhere, even in the apparent emptiness between stars. To understand how energy can lurk in empty space, let us take a closer look at those particles that come in and out of existence in the quantum vacuum. They're called virtual particles, and they're really a manifestation of that fuzziness inherent to quantum mechanics. Because of this fuzziness, a virtual particle can pop into existence out of the vacuum for a fleeting moment without violating the conservation of energy. It's like borrowing money, taking out a loan, or making an overdraft on your bank account. In normal life, you can't do this, but in the fuzzy world of quantum mechanics, it's allowed. However, like loans, virtual particles eventually need to be paid back. So after a brief existence, the virtual particle will annihilate, giving its energy to another particle that's waiting around. This constant churn of virtual particles gives rise to the energy contained in the vacuum. So far, so good. But now we bring gravity into the picture. Remember, gravity distorts the fabric of space-time, and it does this in response to the presence of mass and energy. That means that the quantum vacuum should also cause space to curve. It's almost like the vacuum is exerting a gravitational pull, but it can't because the vacuum is, well, empty. This contradiction is at the heart of why gravity doesn't play by the rules of quantum mechanics. Here's what physicists mean when they say that gravity is the curvature of spacetime. Imagine a bowling ball resting on a trampoline. The ball has mass, and according to Einstein's general theory of relativity, that mass warps the trampoline, curving the surface of the trampoline around the ball. This warp is what we experience as gravity. The ball sits at the bottom of the dip, and anything else placed on the trampoline will roll towards it. That's how gravity works. But curved spacetime is a continuous thing. It changes gradually from one place to the next. That means spacetime has no grain to it. It's smooth, and that smoothness contradicts the fuzzy, granular nature of quantum mechanics. The mismatch between quantum mechanics and Einstein's theory of gravity is a huge problem. There are lots of places where these two theories conflict, but the most famous is the Big Bang. Einstein's theory says that at the beginning of time, the entire universe was a single point. But quantum mechanics says that space is grainy and that there's a smallest possible length, so you can't actually have a point. This contradiction highlights a much deeper problem. General relativity and quantum mechanics are two separate theories. They work well on their own, but we don't have a single theory that unites them. That's why physicists have spent the last few decades trying to develop a theory of quantum gravity. It would be a single framework for understanding how gravity works on both large and small scales. And while physicists haven't found a complete theory of quantum gravity, they have several promising candidates. One is called string theory. It tries to explain gravity as the result of tiny, vibrating strings. Another candidate is loop quantum gravity, which explains gravity by imagining space itself as a series of loops. And then there are other approaches that try to show that space-time emerges from something more fundamental, like information or quantum entanglement. But let us focus on string theory and loop quantum gravity, because they address the issue of space being smooth or grainy by making a radical proposal. What if space-time isn't smooth? What if it's full of fluctuations, even at the smallest scales? It sounds crazy, but it makes sense mathematically. Let's take string theory as an example. In string theory, the universe consists of tiny strings that vibrate. Different vibrations of the strings correspond to different particles. But how do these strings explain gravity? Well, in any theory, we expect that a particle with mass should have some sort of energy attached to it. That's because the equivalence principle says that mass is really a type of energy. But adding energy to a string doesn't make it vibrate faster, it makes the string longer. This change in length affects the way the strings interact, and that interaction results in a force that we interpret as gravity. In string theory, then gravity isn't a force that exists between objects. It's a consequence of the stretching and vibrating of tiny strings. To make this work, string theory requires extra dimensions. We can't see these extra dimensions because they recurled up into shapes that are too small to detect. But the mathematics of string theory is elegant. It makes gravity come out correctly without introducing any new particles or forces, and that's why it's so attractive. Loop quantum gravity takes a completely different approach. Instead of thinking of space-time as smooth, loop quantum gravity says that space-time is made of loops. These loops are like tiny threads woven together to form a fabric. This fabric has a grain to it. Space-time isn't smooth. It's made up of little chunks. That means that there's a smallest possible area and volume. The idea is similar to the idea that light comes in discrete packets of energy called photons. We call this quantization. When physicists quantize something, they mean they divide it into chunks or packets. And it turns out that this granularity resolves some of the problems with general relativity. For example, in general relativity, the center of a black hole is called the singularity. The singularity is a place where the known laws of physics break down. It has infinite density and a volume of 0. That doesn't make sense. Nothing can be smaller than a quantum of spacetime, which means that the singularity can't exist. Loop quantum gravity gets around this problem by spreading the mass of the collapsing star over a finite volume. Loop quantum gravity also explains how black holes can grow without limit. In general relativity, black holes grow until their gravity prevents them from gathering any more mass. But in loop quantum gravity, black holes keep growing because there's no shortest possible length. It's a kind of runaway growth that might resolve the problem of the Big Bang too. Loop quantum gravity says that there is a smallest possible length, which means that there is a smallest possible volume. And that means that the universe can't collapse to a point, so there is no singularity at the Big Bang. Instead, loop quantum gravity says that our universe expanded out of a quantum fluctuation from a previous universe. This is called the Big Bounce model. It's an alternative to the hot, dense Big Bang of general relativity. It's important to remember that we don't know how space-time works at the Planck scale. We can't test these theories directly. They're beyond the reach of current technology. We'll need some kind of revolution in physics to get better tools to probe what's happening at the Planck scale. But it's worth pursuing these ideas because they could help us understand phenomena that we can observe. For example, physicists think that effects from the quantum vacuum may be detectable in experiments that study what particles do in strong gravitational fields. Such experiments can be done on Earth with atoms and molecules in extremely precise traps, or they can be done in space with atoms near black holes. This may sound futuristic, but experiments like these are underway right now. They're exploring the interface between quantum mechanics and gravity. And the results could lead to a revolution in our understanding of the universe, because the truth is, the ground beneath our feet is made out of quantum foam. And it is that quantum foam that gives rise to the gravity that keeps our feet on the ground. If you love space, you've probably heard of black holes, but do you really know how they work? We're entering a new era of quantum knowledge. We've come to realize that the universe doesn't always behave as we expect. Ordinary things like water and paper can exhibit surprising quantum properties. These discoveries challenge our intuition and offer tantalizing possibilities for the future of technology. Let us embark on a cosmic journey to see how quantum mechanics shapes our reality right here on Earth. Quantum worlds within us, within things while contemplating the vast expanse of the cosmos. It's easy to feel insignificant. Our planet, after all, is just a tiny speck in an unfathomable universe. Yet when we zoom in, we discover something even more astonishing. The very essence of our being, the stuff we're made of, arises from the same quantum dynamics that govern galaxies and black holes. It's a humbling realization that connects us to the grand tapestry of the universe. At the core of this revelation lies the atom, the fundamental building block of matter. Inside these minuscule structures, electrons whirl around a nucleus in specific energy levels. Here's where the strangeness of quantum mechanics comes into play. According to classical physics, an electron should spiral inward due to electromagnetic forces. But observations show otherwise. Electrons remain in their designated levels. Why enter the Pauli exclusion principle? Quantum rule asserts that no two electrons in an atom can occupy the same state. So this principle isn't just a quirk of nature. It's the bedrock of the periodic table. It dictates how elements combine and form compounds. Without this quantum constraint, the chemistry that sustains life couldn't exist. No stable molecules, no chemical reactions. Life as we know it would cease to exist. But the marvels of quantum mechanics don't end there. Consider the double-slit experiment, one of the most iconic demonstrations of quantum weirdness. When particles like electrons are fired at a barrier with two slits, they don't pass through the slits as individual projectiles. Instead, they spread out like waves, creating an interference pattern on the screen behind the barrier. This wave-like behavior is a testament to the inherent uncertainty of quantum nature. It underscores the idea that we can't precisely know both the position and momentum of a particle. The very essence of quantum mechanics is woven into the fabric of our being. We are, in a sense, quantum creatures living in a quantum world. Quantum leaps, how we harness quantum weirdness. Our journey through the quantum realm reveals just how deeply this mind-bending physics intertwines with our lives. It's not just a theory confined to distant galaxies or theoretical musings about the universe's dawn. It's an integral part of our everyday experience. Take, for instance, the Hubble laser, a device that has revolutionized everything from barcode scanners to laser shows. At the heart of a laser lies stimulated emission, a quantum phenomenon predicted by Albert Einstein in 1917. This process involves a photon triggering the emission of another identical photon. Without this quantum leap, lasers wouldn't exist. And lasers have become indispensable in fields from telecommunications to medicine, enabling precise surgery and countless other applications. Zooming in further, consider the transistors in your smartphone. These tiny switches that control the flow of electricity exhibit properties that can only be explained by quantum tunneling. Electrons can pass through barriers even if it seems classically impossible. This seemingly magical ability underpins the digital age. Without quantum tunneling, we wouldn't have the computers, smartphones, or internet that dominate our lives. The impact of quantum mechanics extends even to the Global Positioning System, GPS. Satellites that help us navigate rely on atomic clocks. These clocks measure the quantum transitions of electrons within atoms to keep time with unparalleled precision. Without this accuracy, GPS would be significantly less reliable, impacting everything from navigation to communication. And let's not overlook the Hubble LED bulb. The familiar glow of your bedside lamp results from electrons transitioning between quantum energy levels. When electrons drop down these energy levels, they release photons of light. Understanding these quantum leaps has allowed us to create more efficient and longer-lasting light bulbs. Our dependence on quantum mechanics becomes even more apparent when we consider medical imaging techniques like MRI, magnetic resonance imaging. MRI machines harness nuclear magnetic resonance, a purely quantum effect, to produce detailed images of the human body. This technology has revolutionized medical diagnosis, helping doctors spot issues that would otherwise be difficult to detect. From the transistors in your phone to the lasers in a barcode scanner, quantum mechanics isn't just a curiosity. It's a powerful force shaping our daily lives. Quantum in nature, where life meets quantum weirdness. The marvels of quantum mechanics do not end at the boundaries of human innovation. They extend deep into the very essence of nature itself. The organic world, with its intricate processes and delicate balances, also relies on the principles of quantum physics. Consider photosynthesis, the process by which plants, algae, and certain bacteria harness sunlight to create energy. This remarkable process occurs with astonishing efficiency, up to 95%. Recent studies suggest that the secret behind this efficiency lies in quantum coherence. Within the molecular structures of plants, energy can sample multiple paths simultaneously, effectively searching for the fastest route to the reaction center. This quantum advantage allows organisms to convert sunlight into chemical energy with unmatched effectiveness. But quantum influences on the living world go beyond efficiency. Some migratory birds, including starlings and indigo buntings, appear to use Earth's magnetic field as a compass. Their ability to navigate over vast distances with incredible accuracy has long puzzled scientists. Research indicates that certain proteins in the bird's eyes contain quantum dots. These particles exhibit quantum properties that allow them to sense magnetic fields. By exploiting quantum entanglement, birds literally see the magnetic field lines guiding them on their journeys. Even within our own bodies, enzymes, the catalysts that facilitate biochemical reactions, sometimes employ quantum tunneling. Reactions essential for life could not occur at the necessary rates without this quantum boost. In essence, we're all, in a sense, products of quantum mechanics. The carbon in our bodies, the ATP that provides energy, the DNA that carries our genetic code, all came into existence through processes governed by the principles of quantum physics. From the tiniest bacteria to the largest whales, life as we know it depends on the rules of quantum mechanics. Quantum connections, our enduring bond with the quantum realm as we continue to peel back the layers of reality. The bond between quantum mechanics and our existence becomes ever clearer. We're not just observers of this strange quantum world. We're active participants. The sun, the celestial powerhouse that sustains life on Earth, owes its ability to shine to quantum tunneling. Without tunneling, the protons inside the sun could not overcome their mutual repulsion. Nuclear fusion, the process that powers the sun and gives us light and heat, wouldn't occur. The very existence of Earth as a habitable planet would be impossible. The elements that make up our planet, from the iron in its core to the oxygen in its atmosphere, were forged in the hearts of stars. These stellar furnaces rely on quantum mechanics to produce the building blocks of our world. But perhaps the most profound connection lies in the very essence of quantum mechanics itself. The principles that we observe in the subatomic realm mirror the workings of the universe on a grand scale. Consider the behavior of galaxies. Like the wave-like behavior of electrons, galaxies exhibit properties that defy classical expectations. They rotate, collide, and interact in ways that can only be explained by quantum mechanics. In a sense, the quantum nature of the cosmos reflects the quantum nature of our own existence. The rules that govern the behavior of particles on the one hand mirror the behavior of galaxies on the other. As we delve deeper into the quantum mysteries of our world, we uncover a reality more wondrous and interconnected than we ever imagined. From the smallest subatomic particles to the grand sweep of galactic interactions, quantum mechanics weaves a tapestry of existence. And we, with our insatiable curiosity and thirst for knowledge, are forever bound to its enigmatic embrace. Our journey through the quantum cosmos is just beginning. The more we explore, the more we discover the profound connections between the very small and the grand expanse of the universe. Or the quest to understand the quantum realm isn't just a scientific pursuit. It's a testament to our enduring curiosity, our desire to comprehend the symphony of existence. Each new discovery brings us closer to the heart of reality. So as we continue to probe the mysteries of the quantum world, let's remember that we are not separate from this grand cosmic drama. We are part of it. The quantum realm is not just out there. It's within us, within the world around us. It's in the glow of a fluorescent bulb, the working of a laser, the function of your phone. Quantum mechanics isn't a distant theory. It's the language of Earth, of life, of civilization. And understanding this language opens up vistas of possibility that were once the realm of science fiction. From new medical treatments to ultra-efficient solar cells, quantum science holds the promise of transforming our world in ways we're only beginning to imagine. The future is quantum, and it's ours to shape. In the 18th century, Galileo Galilei looked through a telescope and found that Jupiter had 4 moons. And that's how humanity became aware that the Earth is not the center of the universe. With the development of more advanced telescopes, we've managed to look further and further into space, studying billions of galaxies and stars and planets and whatever else is out there. And in the last century, we've delved deep into the structure of reality, looking inside the atom to find a world governed by quantum mechanics. We've seen how tiny particles can be in 2 places at once, how they can influence each other instantaneously across vast distances, and how they seem to defy all logic and reason. Now, having uncovered these mind-bending realities, we face a new challenge, trying to understand the universe as a whole by combining the big picture with the very small. There are many theories out there that attempt to unite gravity with quantum mechanics, but as yet, none have been proven correct. Meanwhile, observation plays a central role in quantum mechanics. You can't know exactly where a particle is and where it's going without looking. But that doesn't mean we don't have ways of learning about the universe when we not directly observing it. By carefully selecting the experiments we perform, we can gain insights into the behavior of particles and the evolution of the universe, even if we aren't there to see it happen for ourselves. So here are some of the ways scientists learn about the quantum realm without actually looking. Gravitational waves. Ripples in spacetime in 2015. The Laser Interferometer Gravitational Wave Observatory made headlines by detecting gravitational waves for the first time. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects. They were predicted by Einstein over a century ago, but it wasn't until now that we have the technology to detect them. The LIGO detectors are massive. L-shaped instruments that use lasers to measure the distances between mirrors with incredible precision. When a gravitational wave passes by, it stretches and squeezes space by an almost immeasurable amount. But that's enough to change the distance between the mirrors by a few millionths of a second. That tiny change is enough to trigger a cascade of events that produces a detectable signal. Detecting these waves opens up new ways to observe the universe. Like when 2 black holes merge, they release an enormous amount of energy in the form of gravitational waves. By analyzing these signals, we can learn about the properties of the black holes and test our theories of gravity. Neutrinos. Ghostly particles that speak volumes. Neutrinos are one of the most abundant particles in the universe, but they're also one of the most elusive. They're so tiny and lightweight that they barely interact with anything, including each other, so they can pass through entire galaxies without being detected. But neutrinos are surprisingly useful, because while they're difficult to detect, they do interact with matter extremely rarely. So if you build a big enough detector, you can catch them in action. Researchers have recently proposed a new experiment called DUNE, which will use a 350-meter-long detector in South Dakota to detect neutrinos from the sun. By measuring the properties of these neutrinos, we can learn about the sun's core and test our theories of particle physics. Cosmic microwave background radiation, echoes of the early universe. When the universe was just 400,000 years old, it was hot and dense, filled with a sea of photons that were constantly scattering off of electrons. It was as the universe expanded and cooled. These photons no longer interacted with electrons as often, and they were able to travel freely, creating a snapshot of the universe as it was at that moment. Today, that radiation is known as the cosmic microwave background, or CMB for short. It's incredibly uniform, but there are tiny variations in temperature across the sky. And those variations contain a wealth of information about the early universe. Scientists have used the CMB to map out the distribution of matter in the universe and to study the effects of dark energy. There are new experiments underway to measure the polarization of the CMB, which will will shed light on the conditions in the early universe and help us better understand how galaxies formed. Particle physics. Unlocking the secrets of matter. If you want to understand the universe, it helps to understand the building blocks of matter. That's why particle physicists are working hard to unlock the secrets of the Standard Model, which describes the fundamental particles and forces of nature. One of the biggest mysteries in particle physics is the origin of mass. How do particles acquire mass? Why is there more matter than antimatter in the universe? And what is the nature of dark matter? Particle physicists are also looking for new particles beyond the Standard Model, such as supersymmetric particles, which could help solve some of the problems with the Standard Model. And to do this, they're building ever more powerful particle accelerators. The next generation of experiments will be able to collide protons at higher energies than ever before, opening up new possibilities for discovery. Zooming out, from quarks to the cosmos, one of the challenges of studying the quantum realm is that it's, well, so tiny. But as daunting as it may be to study individual atoms and particles, it's equally challenging to study the universe as a whole. How can we reconcile the bizarre behavior of quantum mechanics with the large-scale structure of the cosmos? It's a question that's puzzled scientists for generations. But recent advances in cosmology have shed new light on the origins and evolution of the universe. By studying the cosmic microwave background, for example, scientists have learned that the universe is expanding at an accelerating rate. This discovery led to the development of the cosmological constant, a mysterious force that seems to be pushing the universe apart. But perhaps even more exciting is the prospect of unifying gravity with quantum mechanics. If we could develop a theory of quantum gravity, it would revolutionize our understanding of the universe, would allow us to study the behavior of black holes and the Big Bang in unprecedented detail. And it would give us a deeper understanding of the nature of reality itself. But don't worry, we don't need to actually look into the quantum realm to make these discoveries. Thanks to the brilliant minds of scientists and the tireless efforts of those who came before them, we have the tools and knowledge necessary to probe the depths of space and time without ever needing to set foot there ourselves. Because sometimes the most profound discoveries are made not by those who seek the familiar, but by those who dare to venture into the unknown. What do you think? Does it feel like we're really on the verge of something great here? Let me know your thoughts. From the tiniest subatomic particles to the grand sweep of galactic clusters, the laws of quantum mechanics govern the universe. For more than a century, quantum mechanics has reshaped our understanding of the microscopic world. But in the 21st century, it has begun to reach upward, touching the grandest questions of all. How did the universe begin? What is space-time made of? What lies ahead for everything we know? Join us as we delve into the cutting-edge science of quantum cosmology. Quantum cosmology. The universe as a quantum system, traditionally. We've studied quantum mechanics in the lab: electrons, photons, atoms. But what happens when we apply the same rules to the universe itself? This is the domain of quantum cosmology. Here, the cosmos is treated not as a fixed backdrop, but as a quantum object in its own right. It could exist in a superposition of many possible states, different geometries, different laws of physics, even different histories. One famous proposal, the Hartle-Hawking no-boundary model, suggests that the universe didn't begin with a singularity at all, but emerged smoothly out of a quantum fluctuation, like a wave function that simply rounded off at the beginning. In this view, the Big Bang wasn't the start of time, but a transition in the quantum landscape. The quantum origin of spacetime, a radical idea now gaining traction, is that spacetime itself may not be fundamental. Instead, it might emerge from deeper quantum processes. Consider entanglements, the mysterious link that allows particles to share information across vast distances. Some physicists, like Juan Maldacena and Mark van Romstonk, have proposed that the very geometry of space is woven from quantum entanglement. In this picture, the smooth fabric of spacetime is like a hologram, projected from underlying quantum information. If true, the universe itself may be less like a physical stage and more like a cosmic computation. Spacetime as an emergent property takes us back to a foundational idea of modern physics. Einstein taught us that mass is another emergent property, arising from the underlying structure of spacetime itself. If spacetime is not fundamental, then the stuff we think of as solid, stable, and real turns out to be no more than ripples on the surface of a deeper, more fundamental reality. Spacetime, quantum information, the new currency of reality, Stephen Hawking. Black hole information paradox: whether information is lost when matter falls into a black hole sparked a revolution. Many now believe the solution lies in treating information as the most fundamental quantity in physics. Energy and matter may be emergent. Spacetime itself may be emergent. But information bits and qubits could be the true building blocks of reality. This has profound implications. It means the universe may operate more like a vast quantum computer than a physical machine. It raises the possibility that existence itself is structured like a code, a program written in the language of quantum laws. This shift in perspective is not merely a theoretical exercise. It speaks to the heart of what we mean by reality. If information is fundamental, then the universe is far from the materialist picture of the past. It is a realm of patterns and relationships encoded in quantum information. Reality becomes less about what things are made of and more about how information is processed and transformed. Future theories. Beyond our horizon, the road ahead is filled with daring possibilities. String theory suggests the universe is composed of vibrating quantum strings in higher dimensions. Loop quantum gravity tries to quantize space-time itself, replacing the continuum with discrete atoms of geometry. Holographic universe. Models propose that our three-dimensional world is a projection from information encoded on a two-dimensional boundary. None of these are proven. All are works in progress. But they represent humanity's most ambitious attempt to unify quantum mechanics with Einstein's relativity and to glimpse the true foundations of existence. These theories paint a universe far richer than our classical intuition can fathom. They suggest the cosmos is not a static backdrop, but a dynamic arena of perpetual creation and transformation. Every point in space-time could be a nexus of countless alternative histories and potential futures. The universe itself becomes a vast reservoir of information, constantly shifting, evolving, and surprising. Humanity's role, from witnesses to participants, so where do we fit in? On one hand, we are tiny, a fragile species on a small planet, orbiting an average star in one galaxy among trillions. On the other hand, we are the only known beings capable of asking these questions, of building particle accelerators, quantum computers, and space telescopes that reach back to the dawn of time. We may even be the universe's way of knowing itself. If quantum cosmology is correct, our role may be deeper still. In some interpretations, observation is not just a passive act, but a participatory one-hour measurements help define reality. If so, consciousness itself could be woven into the fabric of the cosmos. The last horizon, spacetime's fate, looking forward. Quantum theories of the universe also shape how we think about the end of time. Will the cosmos expand forever, its fabric stretching into a cold, dark eternity? Will quantum fluctuations one day create new universes, budding off like branches from a tree? Or could spacetime itself dissolve back into quantum information, leaving only the pure mathematics of possibility? We do not yet know. But one thing is certain: the answers will not only redefine physics, but also reshape humanity's sense of place in the cosmos. As we peer deeper into the quantum heart of the cosmos, we find ourselves confronting not only the nature of reality, but also our own place within it. Are we merely spectators, passively observing the universe unfold? Or are we active participants, our very thoughts and observations shaping the reality we experience? The participatory universe view suggests the latter. It's a humbling thought. Our everyday lives seem so substantial, so concrete. Yet on the cosmic scale, we are both cause and effect, shaping and being shaped by the universe we inhabit. If we choose to see ourselves as separate from the cosmos, then the universe is indifferent to us. We are just here by chance, destined to one day fade into obscurity. But if we recognize our interconnectedness with the cosmos, then we become part of the story. We are not just here, we are here for a purpose. We are the universe's way of knowing itself. As John Archibald Wheeler put it, we are all participants in a great cosmic enterprise, a universe that is self-observing. Closing thought: the quantum universe is not just a theory, it is our reality. Beneath the familiar world lies a stranger, deeper order, where particles flicker in and out of existence, where spacetime itself may be an illusion, and where the future of everything may depend on the rules written at the smallest scales. To study it is to confront the most profound mystery of all. Why is there something rather than nothing, and why does it follow these quantum rules? This is not just science. It is the ultimate human quest. Our journey through quantum cosmology reveals a universe that is profoundly counterintuitive, astonishingly beautiful, and deeply interconnected. It challenges our classical intuitions about reality, showing us a cosmos that is full of surprises, where the familiar laws of physics break down and where the very nature of existence is called into question. Yet amidst these challenges, there is an extraordinary beauty. The universe emerges as a grand tapestry woven from the threads of quantum mechanics. The smallest particles, the vast expanse of spacetime, the enigmatic nature of consciousness all are linked together in an intricate web of relationships. And at the center of this web are we humans, not as detached observers, but as active participants, shaping and being shaped by the universe we inhabit. Our quest to understand the quantum foundations of the universe is not merely a scientific pursuit. It is a journey of self-discovery. As we probe the deepest mysteries of existence, we also learn more about ourselves and our place in the cosmos. We find that we are not separate from the universe, but an integral part of it, or the universe's way of knowing itself. And in that realization lies both the wonder and the responsibility of our existence. If you found this video informative, please leave a comment below. Your feedback helps us make better videos for you. Also, don't forget to subscribe to get notified of future updates. Thanks for watching. See you next time.